Right now, an object NASA tracked for nearly 3 decades has just been caught living a double life. For 27 years, it was filed away as a harmless, predictable asteroid, one of thousands of small rocks quietly looping around the sun, nothing special, nothing to watch closely. Then, in the summer of 2025, it did something an asteroid is not supposed to do. NASA's own tracking system, one of the most precise on Earth, pointed exactly where the math said this object should be, and it wasn't there. It is not a new discovery. It is not a dramatic flyby of some distant moon. It is a small, dark rock that has been quietly orbiting near Earth since 1998, one that most people have never heard of and never will. And it just forced scientists to rewrite what they thought they knew about it. Researchers are not calling this a minor correction. They are calling it evidence of a hidden population of objects we may be completely misclassifying, objects that matter directly to planetary defense, to how we protect this planet. This is the story of asteroid 1998 SH2, and why it turned out not to be an asteroid at all. Here's what's coming. What NASA's tracking system found when the object didn't show up where it should have. What 3 of the world's most powerful telescopes captured when they turned to look at it. And what this means for a whole hidden category of objects we've been misreading for years. I'm Professor John, and this is your channel, NEBULIX. Subscribe now if you want more stories like this, because we're just getting started. The object was first spotted in 1998 and given the provisional name 1998 SH2, a routine designation, one of hundreds handed out every year to newly discovered near-Earth objects. At the time, nothing about it stood out. It was small, dark, and settled into a 1- and 2-year orbit around the Sun, swinging past Earth's neighborhood on a rhythm scientists could calculate years in advance. Between 1998 and 2016, astronomers tracked it well enough, through multiple close approaches, that its orbit was considered thoroughly understood. This is how most near-Earth objects get cataloged. Once enough observations pin down a stable, predictable path, they get filed away, and telescope time moves on to newer, less understood targets. 1998 SH2 became one of thousands of known quantities in NASA's catalog, the kind of object nobody expects to surprise anyone again. Then it went quiet. For 2 full orbital cycles, spanning nearly a decade, no one observed it closely again. There was no reason to. Its path was already on the books. On August 28, 2025, it swung back toward Earth, passing within about 2 million miles of our planet, close enough for NASA's Deep Space Network planetary radar system to get a good, high-resolution look. The plan was routine: point the radar, confirm the position, update the catalog, move on. Instead, the object wasn't where the calculations said it would be. For decades, an object like 1998 SH2 was assumed to move the way asteroids move, governed almost entirely by gravity. That's the fundamental split between the 2 major categories of small solar system bodies. Asteroids are essentially solid rock or metal, with no ice, no venting gas, no outgassing of any kind. Their paths are shaped purely by the gravitational pull of the Sun and nearby planets, which makes their future positions calculable with extreme precision, sometimes decades out. Comets are different. Underneath their surface, they carry ice, frozen water, carbon dioxide, and other volatile compounds. When a comet gets close enough to the Sun, that ice heats up and turns directly into gas, venting out from weak points on the surface. That escaping gas acts like a tiny, uneven thruster, giving the comet a small but continuous push that pure gravity doesn't account for. Over months and years, that push adds up to a measurably different path than a plain asteroid would follow. So, when 1998 SH2 didn't show up where the calculations said it would be, researchers at NASA's Center for Near-Earth Object Studies had 2 options: assume a tracking error, or consider that something else, a force gravity alone couldn't explain, was quietly steering it. If you're the kind of person who likes space stories explained without the jargon, drop a like right now. It genuinely helps this reach more people. To figure out what was going on, researchers didn't rely on radar alone. Radar is excellent at pinning down an object's exact position and distance at a single moment, but it can't tell you much about subtle forces acting on that object over years. For that, scientists turned to optical astrometry, a technique where telescopes precisely track an object's position against the fixed background of distant stars, image after image, across multiple years and multiple orbits. By comparing that real, observed path against the path pure gravity predicted, researchers could measure the gap between the 2, down to fractions of a degree. That gap is called a non-gravitational perturbation, and it's a well-known signature of one specific kind of object: a comet venting gas into space as sunlight heats the ice inside it, giving it a tiny, continuous push that shows up as a small but consistent drift from its expected position. This work was led by Davide Farnocchia, a navigation engineer at NASA's Center for Near-Earth Object Studies at JPL, whose job is essentially to model exactly these kinds of orbital anomalies. The hard part wasn't detecting that gap in the motion, it was proving what caused it. because past images of 1998 SH2 had never shown the telltale tail or cloud of gas and dust that comets are known for. The motion said comet, the picture said asteroid. Hold assumption: 1998 SH2 was a typical asteroid, solid rock, no gas or dust escaping from it, moving on a path shaped only by gravity. New data: David Farnokia and his team measured the non-gravitational perturbations affecting the object's motion and found they were incompatible with it being a plain asteroid. The findings were published in the journal Nature Astronomy. To understand how small these perturbations can be, it helps to look at a comet we've studied up close before. When the European Space Agency's Rosetta mission orbited Comet 67P Churyumov-Gerasimenko for 2 years, scientists watched outgassing nudge that comet's orbit and even its rotation, in ways that were invisible from Earth, but unmistakable up close. 1998. SH2 never had a spacecraft parked next to it. Everything researchers know about its outgassing had to come from tracking its position from tens of millions of miles away, across nearly 3 decades. Scale comparison: this is an object that had been tracked accurately for nearly 2 decades. And one small, consistent nudge in its path, invisible to anything but precise, long-term tracking, was enough to expose it. It's the equivalent of noticing someone is quietly favoring one foot after watching them walk for 20 years. Why it matters for us? This is exactly the kind of subtle deviation that matters when scientists are trying to predict whether a near-Earth object could ever be on a collision course. Missing a force like this means missing part of the object's real future path. And for planetary defense, close enough isn't good enough. Hold assumption: if 1998 SH2 were really a comet, its tail and coma, the gas and dust cloud around a comet's core, should have been visible in earlier images. They weren't, which is exactly what made this object so confusing for years. Every close approach since 1998 had been photographed by capable telescopes, and none of them had caught so much as a hint of a tail. New data: when the object made its close pass to Earth in August 2025, researchers seized the narrow window and requested observations from 3 major observatories simultaneously: the Canada-France-Hawaii telescope in Hawaii, the European Southern Observatory's Danish telescope in Chile, and the ESO's Very Large Telescope, also in Chile. Coordinating 3 telescopes across 2 hemispheres for a single fast-moving target isn't trivial. It requires precise timing, since the object's brightness and visibility change by the day as it moves. According to Olivier Hennaut, an astronomer with the European Southern Observatory and co-author of the study, the images collected showed a weak but clear tail, directly confirming that 1998 SH2 is in fact a comet. Scale comparison: this wasn't a bright, obvious comet tail like the ones you might picture streaking across a night sky. It took some of the most powerful ground-based telescopes on Earth, aimed at exactly the right moment during exactly the right approach, to catch a signal faint enough that ordinary observatories had missed it for 27 straight years. Why it matters for us: the object has now been given a new designation, P1998 SH2, officially reclassifying it as a comet. That's not just bookkeeping. It changes how scientists model its future orbit, its long-term behavior near Earth, and every prediction built on the old asteroid assumption. Drop a comment if you'd never heard of a dark comet before this. It genuinely helps me figure out what to cover next. Hold assumption: objects that show no visible tail or coma, but do show irregular motion, were being treated as strange edge cases. Asteroids with unexplained quirks, not a distinct category worth naming or studying systematically. New data: these objects are now recognized as dark comets, a class first identified in 2016, with roughly a dozen more found since. Researchers sort them into 2 rough groups: larger ones on orbits similar to short-period comets, spending most of their time farther from the Sun, and smaller ones that stay closer in on tighter, warmer orbits. Both groups share the same giveaway: motion that doesn't match pure gravity, but differ enough in size and orbit that scientists suspect they may not share a single explanation. Researchers now suggest that many of the larger dark comets, including objects like 1998 SH2, could turn out to be regular comets, if astronomers simply get the right opportunity to observe them with powerful enough telescopes at the right moment. In other words, the dark in dark comet may often just mean not yet caught in the act, rather than a genuinely different type of object. Scale comparison: this means an entire population of near-Earth objects currently filed under Asteroid may actually be quietly venting gas, nudging their own orbits in ways our current models don't account for. A filing cabinet mistake potentially affecting objects that pass this close to Earth. Why it matters for us: Farnokia put it directly: Because of outgassing, the motion of comets is perturbed more significantly than that of asteroids, and detecting those perturbations is an important diagnostic tool for planetary defense, helping scientists understand which objects may be comets rather than asteroids, how their orbits evolve, and how that affects the risk they pose to Earth. Picture the moment those 3 telescopes locked onto that faint object, 27 years after it was first spotted, and given a name nobody thought twice about. For almost 3 decades, it looked like nothing more than a rock on a predictable loop around the Sun, tracked, catalogued, and forgotten. Then, for one narrow window in August 2025, sunlight finally caught it doing what it had probably been doing all along, quietly venting gas into space, nudging its own path by fractions of a degree, hidden in plain sight the entire time. It raises an uncomfortable question. How many other objects in NASA's catalog are sitting under the wrong label right now, simply because nobody has pointed the right telescope at them at the right moment? NASA's upcoming NEO Surveyor mission is being built specifically to catch more objects like this, the ones too faint or too dark for older telescopes to have ever noticed. Scanning the sky in infrared, where outgassing and faint comet activity are easier to detect. Which means 1998 SH2 likely isn't alone. Somewhere out there, more objects wearing an asteroid's name are quietly living a comet's life, waiting for the right telescope at the right moment to finally catch them in the act. If this is the kind of story you come here for, subscribe and turn on notifications, because we're going deeper into planetary defense next time. Drop a comment with what surprised you most and share this with someone who needs to hear it. Thanks for watching.